And our last topic is catalysts. A catalyst is a substance that increases the rate of the reaction, but it is not consumed. So, catalysts make reactions go faster, and when we put in the catalyst is left over at the end of the reaction. So that's what we mean by not consumed. And this also leads to the term catalytic amount. You might see this used in um, lab instructions or referred to in papers. A catalytic amount just means a really small amount. Like it's not going to get used up, so you just need a tiny amount to get it to go. The catalysts, we can have them in a bunch of different forms. So a homogeneous catalyst means something that is in the same phase. So an example of this, there are a lot of reactions that are acid catalyzed. That just means that you need to have some acid in the solution, right? That's going to be some dissociated acid. Probably you're going to use a strong acid and you will have H plus in solution. It's all in the same phase. Or you could have a heterogeneous catalyst, which is in a different phase. And so this is usually like a charcoal surface or a glass surface or a solid surface that has had something painted on it that can grab whatever's happening in solution and assist it through the process. The way that catalysts work is by lowering the activation energy. It can be in a bunch of different ways. And enzymes are a great example of catalysts that exist in your body. What most enzymes do is make things line up properly. So that collision part of the collision model that goes into the frequency factor is overcome when an enzyme holds something in the correct orientation for the reaction to happen. That's how it makes it go more quickly. And in some cases, it's the only reason it goes at all is because of the enzyme. So let's do an energy diagram. I mean, why not? So our normal path, reactants to products, I've drawn this exothermic. It could be endothermic. I have my activation energy of the normal path for my reaction. The catalyst what it does is lower the activation energy. So the reactions are the same, the products are the same. I just have a smaller barrier to get over. So that's what this orange line shows is a lower activation energy in a one-step path. It's also possible that you can get some sort of alternate path for the catalyzed reaction. And so I've kind of hidden that under here in purple. This is an example where I get over the energy barrier and form an intermediate and then have to do a second step to get the reaction to complete. But I still start and end at the same place, and I have lowered the activation energy overall for any of the steps that I'm doing.